All right. Thank you for the introduction, and I would like to thank the organizers for inviting me to the conference, and it's been a fantastic experience listening to so many wonderful talks over the last 1 week. So thank you once again. So what I'm going to talk about today is, of course, continuing with the idea of twisted bilayer graphene, but with a slightly different idea and in a different regime from what we have heard from different speakers over the last week or so. So right at the outset, let me acknowledge my collaborators. So this work was done in collaboration with Marcus Kinderman at Georgia Tech, along with 2 graduate students, Stephen Spitz and Stephen Carter. And the talk that I'm going to give right now is based on these 2 works. And I would like to, of course, acknowledge support from the grant agency. So being a speaker in the second week of the conference, I was sort of not sure how much introduction would be a good introduction and not lose half the audience who was there for the first week. So in lieu of that, I thought, why don't I just flash the main result right at the outset? So if you are an expert, you can go to sleep after this. Okay? So here is the idea. The idea is that if we know that the conventional understanding so far is if we have twisted bilayer graphene, there are 2 regimes, small angles and large angles. It is in this regime of small angles where the layers are strongly coupled, giving rise to flat bands. But in the large angle scenario, the layers are largely decoupled, and there is no flat band and no interesting physics. My talk is essentially disproving this. So what I will try to show you is that in the large angle regime, there is also some very interesting physics. In fact, if you are careful, you will see that here as well, the layers can get coupled, and you will also get flat bands. So let me now go to the introduction. So we all know what the problem statement is, right? So we all know that when we have 2 layers of graphene, we know the usual scenario. You have AA stacking and AB stacking with their respective band structures. The question is, instead of doing this, what if we take the 2 layers and rotate them arbitrarily? What happens? So the current understanding is that if you do that, it's not AA or AB, but arbitrary angle, then what happens is that the Dirac cone is still preserved. Only thing that changes is the velocity, the Dirac velocity, which reduces at small angle but is unaffected at large angle. So here I show you with the dotted curve, this is a numerical calculation of the band structure. The dotted curve is the pristine single layer graphene, and as you see, when the angle is reduced, the Dirac cone is preserved, but the velocity is reduced. In fact, if you plot the velocity, then you see only about 5 degrees from AA or AB, the velocity is strongly reduced, but in this large domain of angles, it's largely unaffected. These were all known around 2007 and 2010, and also in 2011 from Eva Andre's group in Rutgers. They had already seen these things, so they did a Landau level spectroscopy, and you see that the energy goes as root N, root B characteristic of single layer graphene. So they see a nice fit, and when they extract the velocity, they see a slight reduction. Of course, the question is, when you really go to small angle, what happens here? And this question mark was put in their paper itself. It's not I am putting it, okay? They were already curious then. Okay, so this is where the Bistritzer-McDonald paper comes in. So they went to even smaller angles. So alpha here is 1 over theta, which means this is smaller angle. So if you go to really small angle, now we know that numerics tells us that the velocity actually goes to 0, but then keeps going up and down, alternately going to 0 at certain angles, and these are called magic angles. Even though this is single particle physics, it's not completely still understood. I made some attempt at some point, but of course then Ashwin, as he discussed with his chiral model, it's even a better attempt to gain some understanding. Okay, so by 2011, these were all known, and people knew that you could expect some correlation, but the idea was that making samples was very hard until last year. We all know the celebrated pioneering work by the MIT group, which could make a sample near that angle, and they saw correlated insulating phase at half filling and a superconducting phase away from half filling. Since then, of course, a lot of experiments have come out. This is certainly not comprehensive. There are way more. but as we know, it's a very ongoing field with a lot of experiments coming in. Okay, so to gain some understanding why it is that at small angles the velocity reduces and at large angle it doesn't, one can build a simple long wavelength theory for it. So the idea is that if we twist the two layers in real space, then in reciprocal space, of course, the Brillouin zones also rotate, right? So this gives us the length scales and the energy scales in the problem. So this delta k, which is the difference between the k points in the momentum space, this gives me a length scale, which essentially sets the inverse of which sets the length scale in real space for the Moiré pattern, right? And so in order to do a long wavelength theory, we don't want to go too far away from the Dirac cones, which means we require this delta k to be much smaller than the actual k vector, okay? Which in turn means that the angle has to be small. On the other hand, we have two energy scales. One is, of course, the interlayer coupling between the two layers, and then the other scale is something that we can build by multiplying the Dirac velocity with this delta k vector, right? Now, of course, here, well, this is a constant for a given angle. T is changing as a function of r when I twist. So one has to appropriately define what I mean by T here, which I'll do in the next slide. So the typical way of doing, which also Ganpati alluded to in his slides, is that you essentially expand around the individual layer k points, and then you just write down the interlayer coupling Hamiltonian by taking the Fourier of this spatially varying interlayer coupling term, right? So there is a summation over all the Fourier components. And because the Dirac momenta are mismatched, it gives you a delta function which gives you the conservation condition for the momenta, right? So this is Dirac momenta in rotated layer, Dirac momenta in the original layer. This is my difference. But because I'm doing a Fourier over all possible momenta states in the reciprocal lattice, I also have in general g and g theta, right? So that's the total momentum conserving condition. So now, as again Ganpati said, that the assumption here is that you assume that the Fourier of this interlayer coupling falls off very fast with momentum. So then you can keep the lowest order coupling, which I call gamma, and then you choose these vectors such that your delta k is, of course, one delta k that we had, but you can also choose two g's which will simply rotate the delta k and not increase the length. So then what you end up is that you end up with a momentum conserving condition where one Dirac point in one layer is essentially coupled to three Dirac points at a spacing of delta k rotated by 2 pi over 3. And that is essentially what the long wavelength theory tells us with the lowest coupling in the Fourier space. Okay? Now, if this is so, what this means is that if this one layer is coupled to 3 in the other layer, so will this now couple to the other layer, and so on and so forth. So this will keep happening again and again, which means that in this space, each of this is delta k now. This is coupled to 3, this is coupled to 3, that is coupled to 3, and it keeps expanding in this delta k space. So in general, even though I can write the long wavelength theory exactly, in general, the solution is hard to get. Unless you are in this point where you go to the perturbative regime, where you say that this gamma over Vf delta k is less than 1. Then you can just concentrate on the minimum 1 and 3 and exclude all the other points. And then you can do some analytics and you can show that indeed, by doing a perturbative theory, the resultant Hamiltonian is that of a single layer, but with a renormalized velocity. This is single particle renormalization. And the expression is that this new velocity is the original single layer velocity, which is reduced by this factor. And now we simply understand why at small angle this is interesting, because you see that delta k, which scales as angle, so the smaller the angle, the smaller the delta k, this factor becomes larger. So it reduces the velocity more at small angles. But when you go to large angles, delta k is very large. This is not appreciable, and you go back to the original single layer physics. This is essentially a very simple way to understand why small angles are interesting and large angles are not. Okay? All right, so having understood that, I come back to the first slide, the gist, where now we understand why this regime has been interesting and everyone is talking about this, and why this is not interesting. So the question is then, how am I making this claim? So in order to go to our theory and why this is interesting, we need to go back to simple geometry first. So when we mutually rotate the two graphene layers, in general, it could be incommensurate or commensurate, by which I mean I take 2 points and I rotate. There is no guarantee that you will always find another point meeting far away. So when they meet, it is commensurate. When they don't meet, it is incommensurate. Yeah? Now, it turns out in 2010, Jean Millet pointed out that this commensuration can be of 2 types. Any commensuration, you can club them into 2 categories. One is called sublattice even, and this is the case where when you rotate, both AA and BB match. So you start with AA, and then the other commensurate point is also B and B will match. Okay? But there is another scenario where it is also commensurate, but it is only one kind of atoms which will match, only AA, but B and B never match again. Okay? And we know special cases of these things. So this is essentially similar to our AE bilayer, okay? The simplest scenario where A and BB both match. And in AB bilayer, we know that it is only one kind which matches and the other doesn't. So these are generalizations of essentially these 2 kinds which we are all familiar with. Okay, so now what I'm going to show you is that, or rather Millet showed, is that it is not just geometry, but if you now try to understand the band structure, this analogy actually goes even farther. And how does that happen? Well, what you do is that you take the same interlayer coupling term that I showed earlier, and we have this momentum conservation condition, right? Now, the key thing to note here is that if I have something which is commensurate in real space, it essentially implies that in momentum space it is also commensurate, right? Which means that in momentum space, the k and k theta which have been rotated, there will exist some g and g theta for which they will match when I add them. This is the key point, which tells me that if I take this higher g and g theta and plug it in here, I will end up with a momentum conservation condition where now k theta and k are exactly on top of each other. They are not separated, unlike my earlier theory which I had. Okay? So this is going to, of course, come up with a higher Fourier component because I'm adding g, right? So earlier the scale was with t tilde k, which was gamma, and now I have t tilde k plus g, which is v. Okay? And in general, this is going to be smaller, but this will have a new qualitative effect because this is not momentum mismatched. And what is the effect? The effect is that essentially when you do it carefully, you will see that this commensuration physics introduces the mass term in the Hamiltonian, and depending on your kind of commensuration, it will either create a curvature or introduce a band gap. This is what happens. Now, I already told you this is going to be a smaller scale, and in this paper, they did a numerical estimate from ab initio calculations, and it turns out that the only point where this is appreciable is at 38.21 degrees. Okay, this is nothing special. This angle is the angle where, so AA and AB is the smallest lattice vector. You can ask what is the next commensuration which will have the next size of the lattice vector, and it turns out it is this angle. That's the only reason I have 38.21 degrees. Other than that, the theory is general, and what I'm going to talk also is perfectly general. But this is the only point where it is appreciable. And you can see that the scale is roughly 10 MeV, which is 1/10 of the original gamma scale, which was around 10 to the power 2 MeV. Okay? All right. So now if I compare the general scenario of this SEO sublattice and SEE sublattice, you can see that essentially what we had earlier in AB and AA, these are actually special cases of these structures. And the point to note is that in general, SEE sublattice matching has a gap. It is only in the limit of AA where this gap goes to 0. Okay? This is the more general thing. And the other thing to understand, remember is that these always are conjugate pairs. So just as AA and AB differ by pi over 3, one is 0, one is 60, these in general are also at 260 degrees. They're always coming in pairs. Okay, so that is our starting point. That is our starting point for the theory that I'm going to propose. And what made us think is the following. Why is it that people always start, when we talk about twisted bilayers, why do we always start from AA or AB? There is nothing sacrosanct about AA or AB. right, when we were measuring angle. When we have two lattice and we rotate, what matters is whether it's a commensurate or incommensurate. So I'm not talking about the energetics right now. I'm just talking about, if I talk about geometry, right? So in general, then I can think that so this is a typical Moir pattern for a small angle, slightly rotated, and I have very nice interpolation between AA and AB regions and AA regions. But if I take a large angle scenario, let's say I've rotated by a large angle, I don't need to think of it as rotated from AA or AB. I can think of as some small angle deviation from its nearest commensurate structure, right? And so what that would mean is that essentially, whereas here I have an interpolation between AA and AB regions spatially varying, here it is essentially spatially varying of this SEE and SEO regions around which this has been rotated. But I already know that unlike here this guy is going to be gapped and this guy is not going to be gapped, which tells me maybe there is some new physics in this problem. And this is the inspiration here. So if we go along the lines that was adopted in the first long wavelength theory, we can do a very similar thing. So let's say I consider an angle, some theta near some commensuration theta naught, which is not necessarily small. So all these are now order 1, except that this deviation is now very small. Okay? And now I can try to formally expand around the k point as before, and I'll get exactly the same expression. But now I'm going to use the following fact that instead of being restricted to here, I'm going to go to the extended Brillouin zone, and I know that there exists g and g theta where they will merge. And then what this is telling me is that at this angle theta from theta naught, there is a very small vector which in the extended Brillouin zone gives me a small length scale. Here it is large, but here it is not, right? So what I'm trying to say is that this delta k is much smaller than k, whereas your original delta capital K, which was measured from A and AB, was actually of order k. Okay? So then the clue is that, or the way to go about is that then you essentially expand around k plus g instead of k, which we did earlier. And then we have the following: we can use delta k instead of the large delta k. And then the coupling energy scale essentially is reduced to V, which is a higher Fourier coupling, instead of my original gamma, which was at K, right? And if you do it, and if you write down the Hamiltonian, you can show that in real space, this is what it comes out, which is very similar to what you get in the small angle scenario, except with two differences. First, you get a mass term, which is sort of now expected. And you see that this term explicitly has a theta dependence, which means that if this goes to 0 at small angles, this will reproduce our original McDonald and Lopez dos Santos, all those theories. It nicely goes. And of course, the other key factor is that the V, the coupling here, is not gamma, but a lowered coupling constant. Okay. All right, so now that we have that idea, so let's go to the non-perturbative limit, exactly similar to what we had in the small angle case, gamma over V delta K greater than 1. That's where we had all the flat bands. We'll also go to the non-perturbative limit in V over Vf delta K very much greater than 1. So in the real space, so I'm doing this near 38.21 degrees because this is very large here or appreciable. So what this tells me is that although you cannot see by naked eye, essentially underlying this motif, there are interpolating regions of SEE and SEO which are covering the entire region. And as we know, these SEE regions are all gapped out, but SEO regions are not gapped. It turns out if you actually do it more carefully, it is not just SEE and SEO, it also turns out that the lines connecting the two SEO points are also ungapped. Okay, this can be shown. So if you now go from real space to reciprocal space, and because this pattern is on a very large length scale, so I can think of a local band structure at each point in the real space. So I have a real space, this is gapped, this is ungapped. I go to the reciprocal space and I see that at each point in the reciprocal space, there are two Dirac cones. These cones are not from the two different values in the original layer, right? These cones are just split because of the interlayer coupling, because of the two layers, but within each value of the original layer, okay? So there is a whole copy of this for K prime again. Okay, so if I do this, and now if I go back to real space and I consider 3 points A, B, and C slightly away from this line, on the line and slightly away from the line, the band structure essentially looks like this. They open up a gap here, close it exactly on the line, and then open a gap again. And now if you construct an effective low energy Hamiltonian for this in the form of a Dirac Hamiltonian at each of these Dirac points, and you calculate the topological chart, you can show that as you cross from A, B, C, they actually show you a change of plus and minus 1. Plus 1 being here and minus 1 being on the other side. What this tells us is that essentially it means that I have chiral modes which are propagating, and there is a set of counter-propagating chiral modes at each of these nodes, which is percolating throughout the system in real space. So everywhere it is gapped, these are localized and these are chiral, and these are moving along these links throughout in real space. Yeah? And the other thing to remember is that the gap between these two nodes, delta, is actually changing over space. So here they are quite far apart, but at these nodes they merge because they have to, because these are SEO regions which are like these AB regions. So they're merging together. So then looking at this picture, one can then build a network model now built out of these chiral modes because, and we can assume that they are not talking each other anywhere unless they meet at these nodes. Yeah? And that's what we do. So we build a network model built out of these chiral modes, which are talking only at these nodes. So we attach two scattering matrices for each of these nodes, and because it's a hexagonal lattice, there are two inequivalent points. But it turns out that if you use the symmetries of the problem, you can show that indeed these two scattering matrices turn out to be equal. Okay? And the symmetries are as following. So there is a C3 symmetry around each node. There is a mirror reflection along the line joining the nodes, so right there. And there is a point reflection at midpoint of the line joining the nodes, like that. So using these symmetries, you can show that the two scattering matrices essentially reduce to just a one parameter model. So the one parameter, free parameter is lambda, and the alpha and beta here are functions of lambda, and this is a pure gauge which can be gauged out. So we end up with a network model with just one free parameter. And then, because this is a periodic system, you can simply use Bloch's theorem, and it turns out that you can find exact analytical solution for this problem. What does this tell us? It gives us two branches which are dispersive and one branch which is flat. And then this triplet is periodic with pi in energy. Okay? And this is what I have drawn here. Okay? So these two are for these. This is the flat band, and then the whole thing repeats. This is what we get from the expression. So the features of these band structures are there are Dirac points and flat bands, and there is a degeneracy at the gamma and k points in the superlattice Brillouin zone here and there. But the most striking part is that anyone who has worked on frustrated lattices will immediately recognize that this band structure resembles a Kagome lattice, right? And this is very strange. I mean, how did we end up with something like this? So the idea is that it is, if you just think a little bit, it actually makes sense why we are getting something like this. And this is the following. The argument is that the similarity with the Kagome lattice is not accidental. Why? You can think that these chiral modes counter-propagating are all scattering at these nodes and freely propagating elsewhere. So if I go into the limit of very strong backscattering at each scattering center, then essentially I can think of a tight binding model with a lattice point which is not at the node but in the middle of the link. So these things are going, hitting at the node and coming back. And suppose they're not able to move, so then these modes are going to be localized in the middle of the link. And if I build a lattice where the points are in the middle of the link, you immediately see that this is essentially a Kagome lattice, right? So then the emergent lattice underlying this physics is essentially a Kagome lattice, and one comes to the conclusion that indeed the origin of the flat band here is geometric frustration. Okay, so that's what we had from our analytical theory. So we wanted to, how much time? 5 minutes, perfect. We wanted to confirm this in numerics, so we did a tight binding calculation. The only problem is that in order to go to this limit where we are non-perturbative, V over Vf, delta k is very much greater than 1, you need to have or in other words, for these modes to localize very well, you need around 700 lattice constants, which means our lattice has to be around 10 to the power 6. And we found that a bit challenging to do that the tight binding. So what we did was that we just introduced a little artificial interlayer coupling where we artificially bumped up this scale, okay? So what we did is that, so let's say in real space, T is falling off with R like this, the blue curve. We just introduce a little bit of oscillation so that in the momentum space, we have the right, we have a little bit of bumped up value of this Fourier at the right momentum that we need, which is my scale that we need for this problem. That's all we did. Other than that, this is perfectly general. So we did that, and this is what we get. So this is a tight binding calculation. This is near theta 38.546 degrees, which is very near 38.21. And you indeed get a very nice energy dispersion curve, which resembles what we expected from our analytical calculation. And then if we actually calculate the real space localization or the real space charge density, you see it actually gives you a very nice Kagome pattern, which is what we anticipated. Okay, so that brings me to the end of the talk. So just to summarize then, so the gist is here. So when we think about twisted bilayer graphene, the conventional accepted understanding is that it is the small angles where the layers are strongly coupled and you have flat bands, but the large angles are not interesting. But what I'm proposing here is that the large angles can also be very interesting. Indeed, it will also be very strongly coupled and it will give rise to flat bands. But most importantly, the physics here and the ensuing flat bands are very different from what you have in small angles. Okay? And the two key aspects are commensuration and topology, and they conspire in a way to give rise to an emergent geometric frustration. Experimentally, the only point in graphene, at least in twisted bilayer graphene, where to look for these effects would be near 38.21 degrees, and for realistic parameters, it has to be really close. It turns out you have to be close within 0.1 degree. And this 0.1 degree you can understand, because as I said, the scale is 1/10 of the original scale. We see near 1 degree at AA or AB, so this has to be 0.1 degree near this angle. That's the reason, nothing else. The theory is general. It could be very well that in some other system, this scale is automatically much larger, and then it will give you a larger window. But right now, we are constrained with this fact. And finally, of course, because the physics is very different, hopefully there will be new correlation effects which are different from that which are found in small angles. Thank you.
For the talk, questions?
Right. Right. So, right. So as far as I understand, to have effects from boron nitride, they have to be very nicely aligned with the bilayer graphene itself. If it is,
But fairly short periodicities.
I know. So that I know. So the boron nitride has a slightly different lattice constant, but the same thing, same structure. So for this effect to come in, if they are randomly oriented, it is shown that it doesn't have much effect from boron nitride.
Even in your case, it
even in my case.
Okay.
28 atoms instead of 4 from A and AB. So from 4, the next jump is 28. There is nothing in between. Well, I don't know. I mean, you'll have to study the effect there. So it's a frustrated lattice. So but the physics is very different there. Short answer is I don't know. One has to study. For the first time, we have ubiquitous superconductor. Not bad, huh? Yes.
And again, in what way the band is topological?
Sorry, say that again?
Could you explain again in what way the band is topological?
The band is not topological. The origin of the band is topological.
But the band itself...
The band itself is not topological. Of course...
So it has nothing of the topological aspects of the...
Right now it is not. But you know, these in the Kagome lattice, you can gap out with spin orbit and then you can make it a Chern band. So that can be added on top, but at this point, this is not topological.
So at this point, it doesn't even have the fragile topology or anything.
No, 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 no.
Actually, I forgot the question while hearing someone else.
Sorry, what did you say? Oh, you.
I remember the question.
Oh, okay,
yeah.
good, good.
So, just like in case of twisted bilayer graphene, the flat bands have some width. So,
Yeah.
in your case, it is
This
the
is an exact flat band in the limit.
and with the if you consider the effect of external electric field, perpendicular electric field between two layers,
Yeah.
how the electric field will change this, just like the Mandar has discussed the effect of electric field on the bandwidth in the closed angle. So, will it affect at the larger angle in your case?
So I'll have to think, because this is what might happen is that when you introduce an electric field, the symmetries that helped me write the scattering matrices might become different. And then I don't know what will come. But the main thing, but it's not going to be as drastic as what is happening with Mandar, because it's a bilayer graphene there. So in bilayer graphene, when you apply an electric field, it opens up a gap, right? But in single layer graphene, it does not. So it's not going to have that effect for sure.
Let's thank the speaker. Maybe the next speaker can.